molecules that we're building, and we need to discuss geometries. There's two types of geometry I want to talk about. We have the geometry counting everything we see, right, of where everything is on the molecule. What type of arrangement would that be? Whether they're electrons or whether they're actual atoms. And then we have something called molecular geometry, where we only count the atoms themselves. Okay? And we'll go over the difference in those as we go along. But what is the point of this? Why do we need to know the geometry? Where the atoms are arranged in a molecule give you an idea of some of its properties. Right? If the molecule is balanced, we'll call it, where things are perfectly opposing each other, or there's no difference in electronegativity from one side to the other, and so forth. And you'll learn what those terms mean in a few minutes. Then that determines whether the molecule is polar or not. It might determine the color of the molecule, how it interacts with light, or its biological activity, whether a molecule can bind to a particular receptor or enzyme or not, depending on its geometry. Okay, so the first term I want to go over is what's called VSEPR groups. And VSEPR is just an acronym that stands for valence shell electron pair repulsion. Okay, I don't care if you remember that or not, but an easier way to think about it is, from a central atom's point of view, how many groups of electrons exist that are attached to it. Now, a group of electrons may be an actual bond to an atom, because there are electrons over there in that direction towards that atom I'm bonded to, but it also might be one of my lone pairs. So you were drawing your Lewis structures, you notice there were some lone pairs on most of the atoms. Those are also groups of electrons in another direction. So when I count the number of VSEPR groups, or valence shell electron pair repulsion groups, it means how many places, how many directions do I have groups of electrons. So for example, if I'm a carbon atom, and I'm bonded to, say, an oxygen atom, right? It may be a single bond, it may be a double bond, doesn't make any difference. That's just one direction where electrons are, right? It doesn't matter how many electrons are over there. It's just that's one VSEPR group. If I'm that same carbon atom bonded to, say, a hydrogen, yeah, there are far fewer electrons in that direction, but it's still another direction. It's another group of electrons, right? Or if you're, say, a nitrogen atom and you have a lone pair, that's also a separate direction in which you have electrons. So we're going to count every lone pair as a separate direction. For instance, if you're a chlorine, you may be bonded to a hydrogen, right? So it's an HCl molecule. A chlorine bonded to a hydrogen. Very simple, one bond between them. Everybody's happy. The hydrogen has 2 electrons around it. The chlorine has 8 because it's got 3 lone pairs. But from the chlorine's point of view, there are 4 VSEPR groups. Each of its pairs of lone pairs are in different directions. And the hydrogen sitting over there is its 4th VSEPR group. Now, it doesn't really have much molecular geometry because it's just one thing attached to it that's a real atom, so it's kind of simple. But if you looked at the molecule's electronic geometry, from that chlorine's point of view, there are 4 things attached to me, right? 4 regions of electrons. So it has 4 groups attached to it, okay? And for all the examples we're going to cover for this class, you're either going to have 2, 3, or 4 groups attached. All right, is there a question? So I said you'll either have 2, 3, or 4 groups attached. That's all we'll cover for this course, which is the vast majority of our molecules we're going to talk about. So to have 2 VSEPR groups, if you were the central atom and you have 2 groups of electrons arranged around you, are those electrons groups attracted to one another, or since they have the same charge, both negative, do they want to repel one another? Right? And a hit is in the name VSEPR. It's electron pair repulsion. So they're going to try and get as far away from each other as possible. So those electron groups, since there's 2 of them, they want to get as far away from each other as possible around the central atom. So that would be on opposite sides of the central atom. So they're going to arrange around each other with reference to the center atom in a linear fashion. So if you pretend you're the central atom and you hold your arm straight out to each side, that's where those 2 VSEPR groups would be, on opposite sides of the central atom. So we call that a linear arrangement. Okay? If there were 3 groups, what's the farthest 3 things can arrange themselves around a central atom? right? So you're not necessarily stuck to being in a flat plane, but any way you arrange them, right, they will be closer together than if you did put them in a flat plane, right? So the best way to do this is the points of a triangle, right? So if you have a central atom, you put an electron pair in one direction, let's say straight to the left. The next two will also be in that same plane, right, perfectly flat, but now not necessarily straight to the right or up or down, but they'll be spaced in an equilateral triangle. So imagine it as a Mercedes logo, right, with the 3 points where they meet, or the points that meet the circle. That's where those groups will be compared to the center, right? They'll be in a little triangle arranged around the center. So we call it trigonal planar. Trigonal indicating a triangle shape, planar indicating it's in a plane. They're all in the same flat plane. All right, let's move up to 4. This one requires a little more three-dimensional thought. Right, if I put 4 groups around it, they don't form a cross. Right, there aren't 2 where it's above and below and then 1 on left and right. They can get farther apart than that. We form what's called a tetrahedron. Right, so these 4 groups, we might draw them on a flat piece of paper as above, below, left, and right, but they do exist in 3 dimensions. So in this case, they will move out of the plane and get a little farther apart from each other. And I have a little video I linked on your Discord to show you an example of all those types of arrangements, because it's hard to do on a 2-dimensional surface without some drawing techniques. But if you look at it in 3 dimensions in a video, have it spinning for you, you'll see what I'm talking about. If you also have access to one of these molecular modeling kits, you can put those together. Some of the atoms in there have tetrahedral geometry. For instance, pick a carbon, and put 4 single bonds on it, and you'll see how those 4 groups are arranged in a tetrahedral manner. Okay. So here's a way of drawing that on a flat piece of paper in 2 dimensions. The linear one's pretty easy to draw. You see the number of steric groups there is listed as 2. And so they'll be on opposite sides of the central atom, listed as E here. And this angle between the 2 will be 180 degrees. They're on opposite sides. So it's a straight line. For 3 Vesper groups on the far left, we have 3 X's, 3 molecules arranged around a central atom, labeled E here, in a flat plane, so it's pretty easy to draw on the screen. And the angle between them would be 1/3 of 360, so 120 degrees. Just like I described, it looks like the edges of a triangle. And then the last one at the bottom, tetrahedral, is kind of difficult to draw on a 2-dimensional surface because it's not flat. Right? So we tend to draw it with those wedges and dashes. And what those things mean is the wedge, the little triangle-shaped bond, means that X is kind of facing out of the plane of the board. It's coming towards you. Whereas the X with the little triangular dashed lines means it's fading away from you into the background. Right? So if you look at it in 3 dimensions, imagine it in 3 dimensions, the 2 X's on the top and the right are in the plane, whereas the others are facing either coming towards me, but not directly towards me, but kind of at an angle, and the other one is fading away at an angle. And if you measure those angles, they're all 109 degrees for a perfect tetrahedron. Okay? And I just went over the columns on the far left there, whether it was 4 or 3 or 2, respectively, number of actual atoms attached, but sometimes atoms have lone pairs. Right? We drew some Lewis structures where you ended up with some lone pairs, not very common on carbon, but on things like nitrogen and your halogens and things like that, and oxygen in particular, you're going to have some lone pairs, 1 or more. And so if you have 1 lone pair, shown in the center of that little table, that lone pair acts as another Vesper group. It is a group of electrons. So overall, that thing has 3 Vesper groups. The 2 X's, as shown here, right? The 2 actual X's bound to the E in the center, and the lone pair at the top. Well, the lone pair is not a real atom, but it does take up space, right? It takes up physical space. It has negative charges associated with it. So the 2 X's and that lone pair don't want to get near each other. So it's going to act as if it's another group of electrons, right? They're going to space around the center in this trigonal planar arrangement. So overall, if you have 3 Vesper groups, whether it's 3 real atoms or 2 real atoms and a lone pair, it still has this trigonal planar electronic geometry. See how they're all spaced the same way. But when we talk about molecular geometry, make sure you get those straight. electronic geometry, it's still trigonoplanar because I'm counting everything electric, everything with a charge. But molecular geometry, I'm only going to look at the atoms. So imagine covering up this lone pair. It still had an effect, I agree, on pushing these two from not being linear. It pushed them down this way. But now we call it angular or bent. Okay? So the whole thing still has trigonoplanar geometry electronically, but molecularly it has a bent or angular geometry. And in fact, this lone pair takes up more space than the atoms do because there's nothing restraining them. Right? It's a big orbital out here, as you see drawn in these figures over here. It's a big orbital. And it bends these two away from being linear more so than if it were just a regular atom out there. So if it were just three regular atoms, they're all 120 degrees apart. But when it's two atoms and a lone pair, this takes up more room. So it pushes these two x's a little closer together, so the angle's a little less than 120 here, and these two angles will be each a little more than 120. I'm not going to ask you how much more or how much less, just know that that effect occurs. Right, in the example on the bottom, we have tetrahedral. The angle's around 109 degrees. Right? It's in fact 109.5, but that's okay. It's 109 degrees for what you need to know. But if one of those x's, being four of them, was a lone pair, or if two of them were lone pairs, this whole thing still has tetrahedral electronic geometry because there's still four electron-containing things around it. But when you talk about the molecular geometry, we have to say what it really looks like if you don't look at the lone pair. So the one in the center, right, we have four electronic things, so it definitely has a tetrahedral electronic geometry. In fact, all of these in this row do. But this one, if I ask for its molecular geometry, I'm going to cover up the lone pair, don't look at it. It looks like these three are forming the base of a triangular shaped pyramid. Right, so the three x's are actually on the ground, imagine that. And then the E is the point of that pyramid. Now there's a lone pair hovering above the pyramid. Right? That's kind of what's going on over here. It's a triangular shaped pyramid. There's an E at the apex of the pyramid and then an X above it. But all the angles here are 109 degrees. So you could flip this pyramid onto any side and it all looks the same. In this case, there is no X above the apex of the pyramid. It's just a pyramid. And if you flip it on its side, it won't look very nice because this X won't be pointed up. Right? So because this lone pair takes up more space. So it's a little unusual. If you cover up the lone pair, it has this shape called a triangular pyramid. Right? So it's a trigonal pyramidal is what we call it. Not trigonal planar, that was over here. These three are in the same plane. None of these are in the same plane. Right? So it's called a triangular pyramid, or trigonal, meaning triangle again, pyramidal, or pyramid, right, is the shape. If you have two lone pairs and two real atoms, overall it still has four Vesper groups, and overall it would still have this tetrahedral electronic geometry. But in this case, if we look at just the molecular geometry, ignore the lone pairs, they had an effect on bending this, but now these three are once again in a straight, not straight line, but bent line, or same plane again. Right? So we call it angular or bent once again. But this angle will be far less than 120. In fact, it's less than 109, much less, probably closer to 100 degrees. Right? Because these two lone pairs, one of them pointing kind of out the board at me here and one behind the board, are pushing these two x's closer to each other. Right? That's shown over here in more of a 3D type drawing. It still has four areas of electrons, so the electronic geometry for all of these is tetrahedral. Right? But if three of them are real atoms and one's just a lone pair, we get that trigonal pyramid look. Right? Trigonal pyramidal it's called. And if two of them are real atoms and two are lone pairs, we call it bent or angular. Just like this one was bent or angular. Only the angle's more acute here than it was here. Right, these are all the geometries I want you to know. There's a video here that I posted on the site for you to watch, and it's much longer and it contains many more types, but the only ones I want you to know are the ones that have 2, 3, or 4 Vesper groups. And that really comes down to only 6 types. You have 2, which is linear, and they can't have a lone pair, of course, because then it won't be linear. If it has 3, it can have no lone pairs, or 1, giving you a trigonal planar molecular geometry, or a bent molecular geometry. In either case, it still has a trigonal planar electronic geometry. Or the case where we have 4, which gives you several options of having 0, 1, or 2 lone pairs. In every case here, these are all tetrahedral electronic geometries, like this little diagram indicates. But then it could be tetrahedral, trigonopyramidal, or bent molecular geometries. And so keep those 6 in mind. That's the only ones you have to know. Right? There are many more in this little video, but that's the only 6 we're going to talk about. Right? So let's do a couple examples. Let's do some with 2 Vesper groups, which you know those are all linear. The easiest way to get 2 things who repel each other away from each other is to put them on opposite sides. So if you were to draw the Lewis structures, which I suggest you do, and one of these we did in our example earlier today, we did this one last time, I believe, CO2 and hydrogen cyanide. Let's draw both of those Lewis structures out. If you draw the carbon dioxide out, you're going to have to promote some lone pairs to make double bonds to fill the octet of carbon, but you end up with this type of thing. Now, yes, there are multiple bonds to oxygen. In fact, this carbon is making 4 bonds to oxygen, 2 here and 2 here. But the number of Vesper groups, number of regions that contain electrons, is still only 2. Right? The carbon has no lone pairs. Right? It has a region over here bonded to an oxygen. There's a lot of electrons over here, but there's only one region that this carbon is connected to, and only one region over here it's connected to. So it only has 2 Vesper groups. These lone pairs on the oxygens are not on the carbon. They're on this oxygen, so they're not a separate group as far as this carbon is concerned. Okay? So this thing has 2 Vesper groups from the carbon, so therefore it has linear geometry. Right? Both molecular geometry and electronic geometry. And those 2 will always be the same. If there's only 2 groups, there's only one way to do it, and it's linear. Okay? For hydrogen cyanide, if you draw the Lewis structure, we'll end up with a triple bond between the carbon and nitrogen, right, to fill the octet of carbon. Here again, the carbon only has 2 Vesper groups. There's the hydrogen over here and the nitrogen over here. Yes, there's more electrons on this side than there are on this side, and we'll get to that later when we talk about the polarity of this thing. But for now, this has linear geometry. Right? There's 2 groups, one on the left, one on the right. Right? And there's no difference as far as the carbon is concerned in counting them. There's 2 of them. One doesn't count more than another. We'll talk about polarity a little later. But there are 2 Vesper groups. Right? There are no lone pairs. So again, this thing is linear. Right? So let's move on to a more complicated example. We have 3 Vesper groups. This falls into 2 categories. Right? 2 Vesper groups only had 1 category, always linear. 3 Vesper groups could fall into 2 categories. In all these cases I'm going to show on this slide with 3 Vesper groups, they all have trigonal planar electronic geometry. Remember, that just counts how many things are there. But one of those things might be a lone pair. So in the case where we have 0 or 1 lone pair, that makes our 2 categories here. So on the left, we'll do the one where there's no lone pairs. That's our formaldehyde. If you were to draw out the Lewis structure, the carbon's in the center, and I have 3 things attached to it, each hydrogen and the oxygen. So it has 3 Vesper groups. There are no lone pairs. So if we try to draw this, we get something like the figure on the left. We're going to end up promoting one of the lone pairs off the oxygen to fill the carbon's octet. So go through the steps of your Lewis structure drawing to see that. But from the carbon's point of view now, there are 3 regions of electrons. The 2 hydrogens and the oxygen. I know it's a double bond, and yes, there are lone pairs on the oxygen, but from the carbon's point of view, that's just one thing over there that has electrons in it. Okay? The carbon itself has no lone pairs, so there isn't a 4th thing to count. So there are only 3, so it adopts a trigonal planar molecular geometry. Okay? And in the other example here where we do have a lone pair is sulfur dioxide. So if you draw that out, our sulfur ends up bonding to each of the oxygens, right? And then we put the lone pairs on all the oxygens, and we end up with an extra lone pair, so we throw it on the sulfur in the center. But not everybody's happy. We haven't filled the octet of these things, so you have to promote one of the pairs of electrons on the oxygen, either one, to a bond and make a double bond between the oxygen and sulfur. So now we have octet filled for this oxygen, the octet filled for the sulfur, but this oxygen over here also has 8 around it, so we're happy with that. Right? Everybody has 8, we're all good. And if we look at the number of things, the number of electron regions around the sulfur, we have this oxygen, we have the other oxygen, and we have our lone pair. None of these other lone pairs are on the sulfur, so we don't count those, right? Only the ones on the sulfur are regions from the sulfur's point of view. So we have each oxygen and the lone pair, so there are 3. So this has overall, electronically, a trigonal planar geometry. But if you ask for...
Question.
Sorry, you have a question? Go ahead.
Yeah, sorry if my audio is...
Sorry, try again.
Go ahead.
Oh, we're both asking the same thing. I think we're both speaking at the same time.
Go ahead.
Okay, why can't there be 2 bonds? Like, I see there's 1 double bond on the oxygen. I just don't understand why there's a lone pair on the top of the S when, like, you could just make another double bond with the other oxygen. That's what I'm confused about.
Okay, so your suggestion is to take the lone pair on the sulfur and make it another double bond to the other O, is that right?
Yes.
Okay, if you did that, let's imagine doing that for a second. Erase that double bond, or erase the lone pair that I have marked, and draw a double bond between, making that S to other O a double bond. How many electrons would then be around the oxygen?
Mm, 8.
So hopefully you can see my mouse. You got these two, these two, these two. They're still there. You said take this lone pair off the sulfur.
No. Take the oxygen one, and then you're taking one of the extra. Like you're making it identical to the left side.
Okay, so take one of these. You're saying.
Yes.
Okay, then how many would be around the sulfur?
8, right?
I think she's wondering why the lone pair is necessary. Like, why it's there in the first place. Why couldn't it just be symmetrical, the right side symmetrical to the left, and then not have the lone pair at all?
Okay,
That
so
looks like they'll have 8 to me otherwise.
Okay, those are two good questions, 2 separate questions. Let's go over both. Let me answer the one we have asked first here. If you take one of these lone pairs, you're saying, and it made the double bond here instead.
Okay.
If that were the case, then this oxygen would still have 8 around it, and I'd be happy, just like this one. But the sulfur would then have 10, right? Because it's got 2 here, 2 here, 2 here. It would have another 2 from the double bond you're making, and the lone pair would be 10, and that's too many.
Why does it need the lone pair?
Well, that was the other question someone asked. If you start from the beginning, and you had SO2, right? You count up all of the valence electrons, right? So how many have we drawn in this figure? Let's count that up real quick. We have 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay. And if I added up the number of valence electrons that these atoms bring to this party, right? Oxygen brings 6, and the other oxygen brings an additional 6, and the sulfur being right below it in the periodic table would also bring 6. So 6 plus 6 plus 6 gives me 18, correct? So we would start off by drawing the sulfur and a single bond to each oxygen. You can walk through this. Right? How many electrons have I used by drawing those 2 single bonds? 4. I started with 18. That leaves me with 18 minus 4, 14. And then I start filling out electrons on the extremities first. So I put 3 lone pairs over here on this oxygen. I put 3 on this oxygen. I still have 2 left over, right? Because I had 14. Putting 3 pairs here and 3 pairs here would be a total of 12. I got to put 1 more pair somewhere, so it goes on the sulfur. That's why there's a lone pair on the sulfur.
Okay, so that's the step I left out. I didn't. I was just making it like happy with 8. I wasn't adding up the electrons, and I forgot that was part of the
so
step.
that's a common.
Thank you so much.
That's a common thing people do. Is they get in a habit of, and there's nothing wrong with it. It's just this. Your brain's trying to make a shortcut, but it doesn't always come out to the right answer. So you're trying to go, hey, things need a certain number of bonds. Just start drawing the bonds. Don't try to do it that way. Put in the electrons on the extremities first, and then promote them as you need. But in this case, when we got to this point in the drawing, when you promoted 1, there was no reason to promote the other because the sulfur would have 10, and if you promoted this one, the oxygen would have 10. So we're done. This is the case. It's finished.
Okay.
It's not pretty. I know. The oxygen over here is not making its 2 normal bonds, but it can't. Okay? So in this case, to go back to our topic here, those were excellent questions, and they built on what we talked about last time. But here we have 3 Vesper groups, once again, when I'm done drawing it. That tells me it has a trigonal planar electronic arrangement, or electronic geometry. But the molecular geometry, that's where I cover up the lone pair and ignore it, it has a bent shape, right? These are definitely pulled down from being straight across. So it's an angular or a bent molecular geometry. Okay? All right, one more to go. Instead of doing 3 Vesper groups, let's go up to 4. In this case, there are 3 categories because we could have 0, 1, or 2 lone pairs. Right? So let's do the case where there's 0 first. That's the easiest. On the very far left, we have methane. And if I ask you to draw its Lewis structure, you throw a carbon down, you put 4 hydrogens around it, and count up all those valence electrons, carbon bringing 4, each hydrogen bringing 1, as a total of 8. When you draw the 4 bonds, you may have drawn them across from each other like a cross, top, bottom, left, and right. There's nothing wrong with drawing it that way as long as you realize that is not its geometry. It's great for drawing the Lewis structures to start with, but when you realize you have a carbon there and it has 4 Vesper groups around it now, it adopts a tetrahedral geometry. Right? So its molecular geometry as well as its electronic geometry is tetrahedral. Okay, so play around with your model kits or watch the video I posted on Discord about showing the molecules rotating so you can see the geometry in 3D. Okay, but what if I have an arrangement where I have 3 real atoms and 1 lone pair? Like if you tried to draw ammonia, and I posted a picture of ammonia's Lewis structure earlier for you. So here we end up with 3 hydrogens attached and once again a lone pair on the center. Because if you count up the number of valence electrons here, it's 8. The nitrogen brings 5. Each hydrogen brings 1. That's a total of 8 because there are 3 hydrogens. And if I draw the nitrogen with 3 single bonds, that takes up 6 of my valence electrons. Hydrogen can't hold any lone pairs because it at max can hold 2, so those are full. So I must put the lone pair on the nitrogen. And that's what I've done here. But then when I'm done drawing, I look at the structure and say, hey, there's 4 areas of electrons around that nitrogen. So it adopts a tetrahedral electronic arrangement. However, only 3 of the things are real atoms. So if you cover up the lone pair and look at what shape it adopts, it has that 3-footed pyramid again, right? So there's 3 at the bottom and an apex where the nitrogen is. So it's going to be a trigonopyramidal type of molecular geometry. You could call it a triangular pyramid if you like. If you can't say trigonopyramidal, I'm totally fine with that. The answer will say trigonopyramidal on the test choices, but if you want to interpret that as triangular shaped pyramid, I'm totally fine with that as long as you understand it. Okay, and then one more case where we have 4 Vesper groups once again, but this time 2 of them are lone pairs in the case of water. So if you draw the Lewis structure of water, you would probably calculate O brings 6 electrons, each hydrogen brings 1. That's a total of 8. I draw the O with a bond to each hydrogen. That's using 4 of those 8 electrons, so I need 2 lone pairs. They can't go on the hydrogen because it's full, so they must go on the central oxygen. So at this point, you're looking at, there's 4 regions of electrons. So once again, like all the others on this slide, there are 4 Vesper groups. So it has tetrahedral electronic geometry. Right? That's what 4 Vesper groups defines. There are 4 regions, so it has tetrahedral electronic geometry. However, only 2 of them are real atoms. So these other things are having an effect, right? The lone pairs are having an effect. They're pushing those hydrogens away from being linear, but it adopts just this little angular or bent shape. Right? And the angle here is much more acute than it was with the 3 Vesper groups being angular or bent, because there's more than one thing pushing those things away.
I have a question.
Go ahead.
Could you explain why the lines are, like, why you're representing them differently? Like, why some are just straight, some are filled in? I'm kind of confused on that.
Okay, so in a 2-dimensional drawing like this, we have to somehow indicate the 3rd dimension. That's all this means. So if you see a straight line, like the 2 on the left here to the above hydrogen and the one going off to the southwest hydrogen, those are represented by straight, simple lines, and they mean they're actually in the plane of the screen or of the board. So the methane on the left, the top hydrogen, the hydrogen towards the southwest, and the carbon in the center are all literally in the plane as you see them. Right?
Okay.
The other 2 hydrogens are not in the plane of the board. So if you can imagine, grab a pen or a pencil and put one end of it at the carbon and put the other end pointed towards this hydrogen, and then pull the pen or pencil towards you out of the plane of the screen. that's where that hydrogen is pointed. Right, so this little wedge, we generally draw it as a wedge like this, indicating that the hydrogen is, as I go from carbon to hydrogen, it's coming out towards me, right? It's coming out of the board in 3 dimensions. So you got to get a spatial geometry going on here. And then the other hydrogen, of course, written with the dashed line, is indicating that if you put a pencil towards it, it's kind of pointed into the board, right? It's fading away from me. That's what these mean. And the same thing with the wedges and dashes over here. This little dash line here is kind of a crude drawing. It should be more of an increasing in size wedge like this one is. This is the proper way to draw it. These are just drawings I found, but it should be more of a increasing line like this.
Gotcha, thank you.
So what's the point of all this? Most of you are like pre-nursing students or future healthcare professionals, and why do I need to know this? Well, if you can imagine a methane molecule in 3 dimensions, that's so much simpler than imagining the organ arrangement inside the abdominal cavity in 3 dimensions. Right? Say you're assisting with surgery later, and someone says, where's the liver in relation to the kidney? Well, when a person's standing or sitting in front of you, it's kind of easy to imagine, but now turn them upside down, flip them over on their back, rotate them around, somebody's arm's all mangled, it's not necessarily hanging by their side. You have to have 3D spatial arrangement in your head. So this is very simple arrangement. You just have 4 things rotating here in your mind. But it gets much more complicated when you think about anatomy. So this is a skill you're going to use. So I'm using it in a very simple context here, teaching you spatial geometries, but you're going to need to learn these in a more complex manner later. So let's use this to teach the basics. So that's why this is applicable to your career as well. Okay, so some trends I'd like
So, sir, Doctor,
go ahead.
When we draw it, do we have to do all the those lines and like the different shapes of line, the thick ones and the arrow ones and all that?
It would be a good idea to learn how to do that. I'm not going to make you draw it for a test, for example. And when you're drawing your Lewis structures, you don't have to draw them that way. But if you finish your Lewis structure from methane and you end up with carbon with 4 hydrogens around it in the cardinal directions and single lines to all of them, there's nothing wrong with that Lewis structure. It's the correct Lewis structure, but it doesn't portray the accuracy of the geometry. So if you draw it with lines above, below, left, and right, each with a hydrogen, and you realize, hey, it's got 4 single bonds, that's okay, it's correct. But when I ask you for the geometry, you need to think that's a tetrahedral arrangement, and I have a question for that that'll help you figure that out. It's coming up in the lecture in a few minutes, so keep that in mind, that it's not really directly across from each other like in the cardinal directions you're drawing. So to answer your question, it's a good idea to learn how to draw these. It'll help you solidify your geometries in your head, the 3-dimensional spatial arrangements, but I'm not going to ask you to do it on a test.
Okay, thank you.
But it would be a great idea to learn how to do it because you won't trick yourself by drawing it a different way. Okay, so I want to go over 3 trends in the periodic table. I posted a very well-made video on Discord for you to watch, but it all comes down to one thing. I'm going to try to explain electronegativity here, but in order to do that, I need to first back up and explain a couple other trends in the periodic table. So here's our typical periodic table, shown on the left here. And if I asked you to ask for the dominant trend in the periodic table is the progression of how big are the atoms, the sizes of the atoms. Okay, so a big atom versus a small atom. And why would an atom be bigger than another? Well, they contain different numbers of protons and neutrons and electrons, right? The protons, and we'll ignore the neutrons pretty much for this class, are all in the nucleus. Neutrons don't add any charge to the thing, but they do add mass, but we're more interested in the charge here. So if I add another proton to the nucleus gains not much in size at all. It's essentially the same size, but it gains another charge, right? It gains another positive charge. And if I add another electron to the atom, it gains another negative charge, but it's filling out a shell, right? So in the first row, if I have hydrogen with 1 proton and 1 electron, it just orbits around it, right? In a very simple way of describing it. And then if I add 1 more proton to the nucleus, and a couple of neutrons we'll ignore, and 1 more electron, the charge hasn't changed, but now those 2 electrons complete the shell in helium. Right? Let's move on to lithium. In the next case, I add 1 more proton to the nucleus, so now they has 3 protons in the nucleus. We'll ignore the number of neutrons for this case. and we add one more electron. Right? So it has 3 protons, 3 electrons. But those 3 electrons can't fit in the first shell anymore. They must now occupy 2 in the first shell and 1 in the next new shell. So it's a larger shell. Think of a next ring around the lithium. It's a larger radius now. So the lithium is a bigger atom, right? Because the electrons fill a bigger shell. And if I move on to the next atom down in the list, sodium, I filled up lithium's shell all the way with 8, so it looks all the way across like neon does. And then I add one more electron, and now it has to fill a 3rd shell. So sodium gets bigger. And if I keep walking down the table with potassium, rubidium, cesium, francium, and so forth, they keep getting bigger and bigger and bigger. So the trend here is I go down the table, down a column, in any column you'd like to pick, it doesn't matter which one. If I go down the column, the atoms get larger. That should make sense because I'm adding to the next biggest shell, which didn't have anything in it before. Okay? If I go across a period or across a row, right? Rows are called periods. So if I go across the row, the number of protons goes up and the number of electrons goes up. But I'm not adding to any new shell, really. It's in the same shell. So it's not getting much larger, but it does get smaller overall. So that seems counterintuitive. How can I add to an atom and it gets smaller? So let's pick an example like oxygen. Right? You see where oxygen is in the table, right? It's one of the areas you had to know. So in the oxygen atom, right, there are a certain number of protons in the nucleus and the same number of electrons around it, right? So in the case, that's the case for every one of these atoms. In the case of oxygen, right, there are 8 protons, right, in the very center, and there are a total of 8 electrons around it, 2 of which are in the lower shell, right? They filled up that really low shell, the one that hydrogen uses. And then there are 6 left over. They fill up the next shell, the 2nd shell. That's our valence shell, because valence always means the outermost shell. So oxygen, having all 8 protons in the nucleus and 2 in its first shell, 6 in its second shell, they're attracted to that nucleus by a certain amount, and they spend their time orbiting around. If I add one more proton to the nucleus, it becomes from oxygen to fluorine now, right? Because now I have that 9th proton down there. And I add one more electron to that outer shell, and as you know, fluorine now has 7 valence electrons, still 2 in the lower shell, but now 7 in the outer shell. And that atom is actually much smaller than the oxygen. The reason being, the electrons in the shells see a much larger charge in the center now. So the nucleus isn't +8 anymore, it's now +9, right? There's another proton down in there. There's a couple more neutrons too, but they don't do anything for the charge. So those electrons floating around in the orbits see a stronger charge in the center, right? 9 versus 8, and they're attracted a little more strongly, so they orbit a little closer, right? They're a tighter attachment, right? Just because there's one more electron doesn't mean it's any farther out. It's in the same shell, but they're all pulled in a little tighter, right? And the video that I linked for you has an excellent video, like demonstration and graphics to show that. So please watch that to help understand it. And he explains it very well. But so that gives you an idea. As you go down the periodic table, atoms get larger. And as you go across the periodic table, left to right, on any one period or row, they get smaller. Taking those two things together, which atoms are going to be the largest? Well, the farthest down the table and the farthest to the left of the table. So in our little diagram here, francium, right, this one here, or cesium, and then francium underneath it, Fr is the abbreviation for it, is the largest atom in this periodic table. Okay? Which atom would be the smallest in the periodic table? Well, that would be helium, right? So it's the highest up in the table and the farthest to the right. So helium is the smallest atom. Francium is the largest atom. Okay, so our trend in atom size goes from top right to bottom left, growing size, the opposite of what you see in this little picture with the arrow. Because this isn't describing size of atoms, this is describing something called electronegativity. You can think of electronegativity as how attracted to my electrons is this nucleus, right? So the nucleus has a certain attraction for its electrons, right? Because positive and negative. And the closer those electrons are, the more tightly bound they're going to be, right? And so the less likely it is to lose that electron. So electronegativity is a measure of that relative attraction. How tightly bound are my electrons? So if you're a really small atom, and they're really close, they're going to be bound very tightly, right? Like helium, right? But helium is unlikely to ever lose its electrons because it filled its shell, just like neon, argon, and all the ones right below it, right? Those noble gases, we call them, right? They're unlikely to lose any of their electrons because they filled their outer shell completely. So we'll ignore those for most of chemistry. They don't do much, right? So everybody else is either 1, 2, 3, 4, 5, 6, or 7 short, except for hydrogen only being 1 short, of filling its shell. So as in the video I linked, you can also take the case of, say, fluorine. Fluorine has 7 valence electrons. It would love to get 1 more and fill that shell, so it just steals them from people, right? So fluorine just steals electrons, right? Takes it from almost anyone. And if you look on the far left of the table, you have things like lithium and sodium and potassium, all in that first row. They have 1 valence electron. They'd happily give up that electron because then that shell is no longer their valence shell. It goes away. It doesn't have an electron in it. And they look like a noble gas from the previous row, right? So that's a perfect marriage. We have our very highly electronegative atoms on the far right, ignoring the noble gases like fluorines, who would love to steal an electron. And we have the ones on the far left who are very willing to give up one. It's a perfect marriage, right? So fluorine and, say, sodium would happily exchange 1 electron. Sodium would gladly give its electron to fluorine to make the sodium ion with a +1 charge. Remember, electrons are negatively charged, so it gave up 1, gaining a +1 charge. Or you can think of it as losing a negative charge. And fluorine gained a negative thing, gained an electron, so it now has a F- a fluoride ion. Okay? Both of those are happy in that arrangement. Okay? So the trend in electronegativity is opposite of the size of the atoms. So the more electrons you have in the larger shell, it's kind of easier to lose the outer shell. And the reason behind that, if you look at, say, a francium atom, that outer shell, that way out there in that 6th shell, right, or 7th shell, it's so far away from the nucleus, right? And it's got all these other electrons in lower shells kind of shielding it from the nucleus. They're kind of in the way. It doesn't really see the nucleus as well. It rather readily can get rid of its its electron, right? Whereas if you look at something like lithium, the outer electron is much, much closer. It's in a lower shell, right? It doesn't have all those shells. So it's harder to lose it. So if you go down in the periodic table, down any one column, the electronegativity gets lower. It's easier to lose your electron, right? Whereas if you go across a row, like we did before, across a period, from left to right, the atoms get smaller, so it becomes more difficult to lose your electron. So if you take those two things together, it's the exact opposite of the sizes. The trend in the periodic table here is as you go up and to the right, we get more electronegative, excluding the noble gases. Right? Well, they don't really, some of them do, and we're going to ignore it for this course, but they really don't participate in what we're talking about. So especially the rows we're interested in, the helium and the neon, do not have any electronegativity. They're happy on their own. They ignore everyone else. So ignoring the 8th column there, from left to right and from bottom to top, we increase electronegativity. So that's the arrow shown on the picture on the left. It's exactly the opposite trend as sizes. Sizes increase as we go down and to the left, and sizes decrease as we go up and to the right. So same thing with electronegativity.
The same thing as like the atomic radii. Is that the same thing?
What's that?
The size of the atom, is that the same? The size of it, is that the same thing as the atomic radii?
Right. Well, when I say size, I really mean the diameter of the thing, right? But of course, that's just double the radius. So you're absolutely right. It's proportional to the radius.
Dr. Mead?
Uh-huh.
Okay, I don't get, why do like lithium and potassium have like different you just said this, but I still don't get it. Why do lithium and like potassium have different electronegativity if it has the same number of valence? Okay,
so you're right, they do have the same number of valence electrons, correct. But in the case of, say, potassium, that valence electron is in the 4th shell, right? Because there's many, many more underneath it. And so it's farther away from that nucleus. Yes, the nucleus does have many more protons as well, I agree. But between the nucleus and that one outer electron are many other shells of electrons which kind of act as a screen or a mask, right? So they're kind of they're kind of making that positive charge in the nucleus look less positive because you have to look through a negative fog. Does that make sense?
Yeah.
So
Thank you.
that's why farther down, you notice it doesn't drop too much as you get farther and farther out, right? So potassium on down to francium, those are rounded off to all 0.9, but they're very, very low, right? What I want you to know is the trend, right? The high numbers on the top right, low numbers on the bottom left. But there are a few numbers I want you to memorize, right? And I've rounded them off to make them easy to remember. Okay, so the most electronegative element will be fluorine by far. It beats all others hands down, right? Let's call it 4.0, right? I know it says 4.1 in the figure, but let's just round it off to even numbers to remember, 4.0, okay? The next most electronegative is the one directly next to it, oxygen. Let's round it off to 3.5. Let's do it in jumps of 0.5. This makes it easy, right? Nitrogen right next to that, let's call it 3.0, right? Carbon right next to that, 2.5. Boron right next to that, 2.0. So those are the region of the periodic table I had you learn, the B, C, N, O, F, right? Basically goes from 2 to 4 in steps of a half. So 2.0, 2.5, 3.0, 3.5, 4.0. And if you memorize that in that very simple step, they're not exactly those numbers, but it's close enough for what I want to teach you, you'll be fine for this course. Okay? The only exact numbered one I really need you to know is hydrogen. And that's the simplest of all of them, so it makes sense. And it is 2.1. I need you to know 2.1, not 2.0. Right? There's a reason for that. We'll get to it in a minute. Okay, so if you memorize hydrogen, it's 2.1, and then boron through fluorine, right, all the way marching up from 2, 2.5, 3, 3.5, and 4, you'll do very well. Right? It's the ones I want you to know. Right? The ones underneath that in the next row, you notice they're the phosphorus, the sulfur, and the chlorines. You could round those off as well as you want. Call them 2.0, 2.5, and 3.0. Right? And after that, they get a little more weird. They're not so easy to round off. But you get the idea that the top three are most definitely fluorine, oxygen, nitrogen, without a doubt. Okay, I want you to know that first row, or second row, and the hydrogen. Okay. What I want you to know about the ones on the far left, all those ones in light blue here, those are all your metals that would love to get rid of their electrons, right? The first and second row there. And all their electronegativities are less than or equal to 1. Right? Very, very small, but 1 or less. Those are the only numbers I really need you to know out of this, but I want you to know the trend.
Is that ionization energy?
Ionization energies are follow the exact same trend, yes, but these are not the numbers for ionization energies. Those are measurements in a unit of energy, right, or in joules or kilocalories or something like that. So they have a unit after them. Electronegativity is a unitless scale. It's based on those ionization energies, yes, but it's a unitless scale where we make a proportion of those numbers and rate the scale from 0 to 4. But they follow the same trend. You're absolutely right. Okay.
Could you repeat the ones really quick that you want us to memorize? The numbers?
I wrote it at the bottom of the little slide here. So if it's in green, I don't care if you know it, right? So it's not going to be useful for our discussions in organic chemistry. If it's not in green, I want you to have an idea of what they are. So all the ones in light blue there on the far left, they're 1 or less. Right? So think of them as very, very low, 1 or less. Hydrogen, I want you to know, is 2.1. Right? And then I want you to know the other elements we're going to talk about almost all the time. The carbon, nitrogen, oxygen, fluorine, across that second row. And you can just step up the scale. It's 2.5, 3.0, 3.5, 4.0. Those are the ones I want you to know.
Okay, thank you.
The ones underneath that, the other yellow ones there, I don't care if you memorize those. You're going to have this chart, of course, for the test. But have an idea that they're not very small, right? They're larger than most of those green ones floating around, right? They're in the 2s to 2.9s to almost 3. So that cluster underneath is not very small, but it's also not nearly as big as, say, oxygen and fluorine. Okay, so no, they're slightly less. They're on par with carbon. Think of it that way. Okay, so if I take two elements from this chart and put them in a bond, which is what we'll talk about now, is bond polarity. Keep this in mind. I'm not talking about the polarity of a molecule yet. We'll get to that at the end. I'm talking about just a bond between any two atoms. So it could be a much larger molecule, but I'm only focusing on two atoms. So I'm going to do 3 examples for you. The top three molecules I have is H2, HCl, and NaCl, sodium chloride. All of these are molecules, but they only have two atoms, right? So make the discussion simple. I'm talking about the bond between the two atoms, not the whole molecule. Okay, so for H2, I look at the two atoms involved, I look at their electronegativities, and I subtract them. Right? So for H2, this should be fairly simple. I take the electronegativity of hydrogen, which was 2.1. I take the electronegativity of the other atom, also hydrogen, 2.1, subtract them, and you're going to get 0. Right? So that should be fairly obvious. If any two atoms are the same atom, right, or if a bond between two atoms and the atoms are the same element, then the electronegativity difference, no matter what the element is 0. Right? So in that case, the electrons are not really drawn to one atom more than the other because they have the same affinity for those electrons, and they have an arrangement like you see on the top left here, this little blue figure. Right? So the electrons spend most of their time equally dividing between the two elements, between the two atoms. Okay? So we call that a nonpolar covalent bond. Right? You already know what a covalent bond is. They're sharing those pairs of electrons, and they're sharing them equally. Why are they sharing them equally? Because they have the same affinity on each side, right? The nuclei of the H and the H look the same, right? So this is a non-polar. There's no polarity to it. They're shared equally, okay? In the case of hydrochloric acid, HCl, let's look at that molecule. The hydrogen and the chlorine definitely have different electronegativities. Let's go back and look. Hydrogen, you memorized, is 2.1, and chlorine was around 3. Right, so 2.1 and nowhere near 2.1, right? They're not the same. So the difference in these two is definitely not 0. Right? So in that case, one of them is more electronegative than the other. In this case, the chlorine is more electronegative than the hydrogen. So this would be the center where the chloride nucleus is, or the chlorine nucleus, and the hydrogen nucleus would be down in here. Right? And you notice the electrons spend more of their time around the chlorine than they do around the hydrogen. So there's a polarity to it. And if I were to zoom out and imagine this, not looking at the electrons themselves, but have some sort of meter nearby that I can measure the charge or the relative positions of the electrons, I would see that they spend more of their time around the chlorine than they do around the hydrogen as they're orbiting around. Okay? That's a crude way to describe it, but it gets the point across. So they spend more of their time around the more electronegative atom. So in this case, if I ask what is the charge on the two ends of this molecule, this end would have a partial negative charge. That's what the little delta means in there. Partial negative and partial positive. Whereas over here on the H2, neither side has more electron affinity than the other, so there's no separation of charge. Here, there's a slight negative tendency towards the chlorine side of the atom and a slight positive tendencies towards the hydrogen side of the atom, right? Because of this polarity. So this molecule, we say, has a dipole moment, right? We're not going to go into the physics of it, but it has a dipole moment where one end looks a little more positive and the other end looks a little more negative, and they will behave like a little bar magnet, right? Where one end will be slightly positive, one end slightly negative. Whereas the H2 over here will not behave as a bar magnet. Each end has the exact same charge, so it just becomes nonpolar. Okay? And in the final case, talking about the bond between sodium and chlorine, I'll go back and look at sodium. It's around 1. Chlorine was one of our more electronegative ones on this end, so 2.9 again. And the difference between those is quite large, right? The difference between chlorine and sodium is 1.9. Right? So that's a very large difference compared to, say, hydrogen and chlorine, which was a difference of only 2.1 to 2.9, so 0.8. Right? So this is a much larger difference. And so, in fact, it's so large that we consider the difference in the attraction between the two is so much that it just gives the electron away. We call this an ionic bond. We talked about this last time. The electronegativity difference is so large between sodium and chlorine that it just gives the electron to the chlorine. And sodium is very willing to do that because it gets rid of its one valence electron. So in this case, because the electronegativity difference is beyond a certain number, which we'll get to in a second, it's an ionic bond. So we have nonpolar covalent, polar covalent, and then so polar, in fact, that it becomes give it away, ionic bond. Right? And I have some cartoons to help describe this. Right? So This helps visualize it for you. A non-polar covalent bond is where the electrons are kind of in a tug of war between the two nuclei, and in this case, nobody's going to win, right? It's an equal tug. They have the same electronegativity. So it doesn't really go anywhere. It's an infinite standoff, right? But in the case of a polar covalent bond, one person's clearly going to win, right? One nucleus has a much stronger pull on the electron than the other nucleus does. So the electron spends the vast majority of its time around one, but the other one still has a tug on it, right? The game kind of freezes at this point. So one of the elements, one of the atoms, in our case of our example, the chlorine, is on the left here, is going to have a much stronger pull on that electron than, say, the hydrogen on the right. Okay, that's polar covalent. And at some point, the tug becomes so strong that you just win. The other one, you rip the electron away. And I have a better cartoon for that one. Is this drawing made by this author back in 2005. And it just kind of describes a ionic bond where one of the atoms completely gives the electron away to the other one, right? And he kind of incorporated that in here. He's very positive about it here, about giving his electron away. There's the little electron. And of course, because he gave away a negative thing, he all has a positive charge. And she's, of course, gaining this electron, and she's very negative about it. All these negative charges. All right. Okay, so where do we draw the line between just sharing the electrons, sharing them with a bias, that's our polarity, or completely giving it away? We have to draw the line somewhere. And it's all based on the differences in electronegativities, those numbers where you subtract them. If you subtract the two electronegativities of the atoms, and the difference is 0, then it's a perfectly nonpolar arrangement. That's all the way on the right here on my chart. So this line represents the difference in electronegativity, 0 being on the right in this drawing. So no difference, right, over here, like H and H in my example. As the difference between the two atoms' electronegativities grows, such as hydrogen and chlorine, we were up to, remember, hydrogen was 2.1 and chlorine was 2.9, so we have a 0.8 difference, or somewhere around 0.7, 0.8 difference. That is definitely in the polar range. But you notice we crossed the barrier. Somewhere in between, we had to draw a line between nonpolar and polar. And that line we draw, we put like a line in the sand, we're going to call it 0.4. Okay? If the electronegativity difference is 0.4 or less, we will call it nonpolar. Right? If it's 0.4 or less, nonpolar. If it's greater than 0.4, so 0.41, 0.42, 0.5, 0.6, and so forth, we're going to call it polar. Right? And then, of course, we need to draw another line somewhere where the difference gets so large, like between sodium and chlorine, that we call it ionic. And that line is not such a strong line in the sand. It's kind of a fuzzy line here. You see there's a gray area. Right? And that depends on what the elements are. So this line we draw in the sand, we said this one was at 0.4, guaranteed. That's always the line in the sand. This one's more of a wide tire track in the sand, right? One side is not the same point as the other. One side here we'll call it 1.5. Sorry, 1.5 here, and the other side will be 2.0, right? And it'll be called ionic if we're beyond 2.0, no matter what the elements are. But somewhere between 1.5 and 2.0 here, we could still call it polar, or we could call it ionic, depending on what the elements are. And I'll show you that in a slide coming up. Okay, so let's do an example of that again. If we have our chart down here, we have hydrogen and another hydrogen. That's our first example. The electronegativity difference was 0, and 0 is more certainly less than or equal to 0.4, so that's going to be called non-polar covalent. Okay, so that was I wrote here, non-polar covalent, still covalent. All right, how do we get to polar covalent? We got to get bigger than 0.4. So that's our H and Cl in our example, hydrogen and chlorine. So hydrogen 2.1, chlorine 2.9, the difference of being 0.8. 0.8 definitely falls in this range of greater than 0.4, but less than 1.5. So anything in those numbers, no matter what the elements are, if it falls in that range, we're going to call it polar covalent, like HCl. Okay? If it's beyond 1.5, right, we have two options. In the 1.5 to 2.0 range, we're going to call it polar if the two things are still non-metals. Like if you have carbon and fluorine. right? So all the stuff in the top corner here are the non-metals, right? The ones I wanted you to know, and hydrogen, of course. Carbon and fluorine, 2.5, and we said 4.0. We're going to round it off. All right, so 2.5 and 4.0. What's the difference in those two? Well, that's 1.5. Right, 2.5 and 4.0, the difference is 1.5. That's definitely in this range, but both of those are non-metals, so that's still a polar covalent bond. If I do something like fluorine and lithium, right, so fluorine over here, 4, and lithium of 1, right, that's 3.0. So I don't care if it's a metal or non-metal, that's definitely beyond 2.0, that's going to be ionic. Okay. The other one, let's do one that's in this range, that's different. So if I pick something like carbon and lithium, right? So carbon 2.5, lithium 1.0. So a carbon-lithium bond has a difference of 1.5, but that's in my range, 1.5 to 2. One of those is a metal, lithium. So carbon-lithium bonds will be ionic, right? They won't be covalent. It's right on the edge, right? So you see, if I go back to my chart here, if it's 0 up to 0.4, we're going to call it nonpolar covalent. 0.4 up to 1.5, most certainly polar covalent. And anything beyond 2, ionic. The only region we got to consider is the width of the tire track here, between 1.5 and 2. If there's 2 nonmetals, we're putting it in the polar category. If one of them, at least, is a metal, right, we're going to put it in ionic category. So that's why there's this gray area in between. And that's what I wrote here. The difference here depends if you have a metal. What constitutes a metal? Everything not in this top right corner, we're going to consider a metal. So all these are metals, right? Except hydrogen, of course. If you want to put hydrogen in its appropriate place in the terms of electronegativity, it should be almost above carbon in this chart. Okay. What if you had a carbon-hydrogen bond? That's another example. Carbon, you're going to see that one quite often in organic chemistry. So carbon 2.5, hydrogen 2.1, and this is why I wanted you to remember 2.1, because the difference is exactly 0.4, and that defines our scale. Right? So this 0.4, a carbon-hydrogen bond, will be defined as non-polar covalent. Okay, so any questions on these, where the numbers leave off? That nice little chart showing it multiple ways. Right, so know where the barriers are. 0.4, 1.5, and 2 are the widths of this gray region. And it depends if there's a metal or not. Okay, so knowing bond polarity. I wasn't talking about a molecule. I used a couple molecules as examples, but they only had 2 atoms. So I want to use it and zoom out and see what is it called when we have molecular polarity. Okay, so when we talk about a bond, either the bond is polar, or it's nonpolar, or it's ionic. Those were our 3 options. When we're talking about a molecule, I'm going to compare all the bonds in the molecule and add them up. Okay, so for example, the one I did below is a C with 3 hydrogens on it and 1 chlorine. So I have a carbon with 4 bonds to it, right? And a quick reminder is, what geometry would this molecule adopt? What's its molecular geometry?
Tetrahedral.
It's tetrahedral, exactly, because there's 4 single bonds, right? 4 Vesper groups and no lone pairs. So that was our first of 3 options for the tetrahedral electronic, and it's also called tetrahedral molecular. Good, that was the bottom left of that chart you saw earlier. So in this case, are any of the bonds in this thing polar or non-polar? So let's look at each bond. The carbon to one of the hydrogens, right? For instance, this one. Is that a polar bond? How do you figure that out? You take the electronegativity of carbon and the electronegativity of hydrogen, subtract the 2, and if I get a number that's less than or equal to 0.4, we're going to call it nonpolar. So this bond, the difference is 0.4, we're going to call that a nonpolar bond. Same thing happens here, same thing happens here. But how about the carbon-chlorine bond? Let's go back and look at those electronegativities. So carbon being what? 2.5. Chlorine, we said we'll round up to 3, right? It's 2.9 something, but we'll call it 3 for our cases here. Even if you call it 2.9 something, the difference here is not 0.4. It's bigger than 0.4. It might be ever so slightly bigger than 0.4, but it is not the same as the other 3. Everybody agree on that? This is definitely 0.4. It's identical to this one. It's identical to this one. This one is larger than any one of those. It is not exactly the same, right? Even though we may call this on the edge of a polar bond, right? These four are not symmetrically pulling on the carbon. And so I want you to think about molecular polarity. Unless all four things on a carbon with four bonds, unless all four things are identical, it is going to be a polar molecule because the chlorine is pulling differently, pulling a little more strongly than the other three. Okay? The example on the right, methane, the carbon with the four hydrogens on it, they're all pulling exactly the same, right? And they're arranged in a tetrahedral, so they're symmetrical about the molecule. So when you have that symmetry of the electrons being pulled from the carbon by all those hydrogens, it's a non-polar molecule. It's perfectly balanced, symmetrical. Whereas on the left, there's an asymmetry, right? The chlorine is pulling differently than the other three, so it's a polar molecule. Okay? Let's do another example. Oh, I didn't draw this one for you. You draw this one out for you. Let's do a carbon with two hydrogens and two fluorines. So CH2F2. Right, and I think I have a picture of it I can grab real quick. It might be on my desktop. Right, so looking at that, you everybody see this, the one in the center? Right, the C with two H's and two F's. Let me pull up all this other stuff so I can keep your comments. Right, so carbon, two hydrogens, two fluorines, right? The carbon-fluorine bond, right, is most certainly a polar bond, right? We go back and look at our PowerPoint. Fluorine being about 4, carbon being around 2.5, that's 1.5. Both of those are non-metals. So absolutely, this carbon-fluorine bond is polar. This other carbon-fluorine bond is polar. The carbon-hydrogen bonds are each non-polar. Right, so the way I drew it on the screen here is deceiving because the carbons, fluorines, and hydrogens are not arranged in a cross like this. That is not how they're arranged. Right, the fluorines are actually, either facing away from us or towards us, and the two hydrogens are in the plane, much like I was showing this one with the hydrogens here. So if you imagine two of these hydrogens are actually fluorine. That's what I'm drawing for you. Okay, so replace any of those two H's with F's. And I ask you, is this molecule balanced? Okay, so if you look at it in my little drawing, it looks like these are not balanced, right? But had I drawn the F up here instead of the H and the H over here instead of that F, it would still be unbalanced because they're not directly across from each other. This is deceiving. They're not a flat geometry. It is actually tetrahedral like this. So put any two of these as F, and you'll notice the molecule is not symmetrical. They're pulling on it, not opposite each other. No two atoms here are opposite one another. So if I have four things attached to a carbon here, and they're not all four the same thing, there's going to be an imbalance. There's going to be an asymmetry. So as long as they're all four are not the same, it's a polar molecule. Right? We'll do a lot of examples in your practice tests. So look at those, and you'll see tons of examples of polar versus nonpolar carbons with four things on them. If it's not all four the same, it's polar. Okay. Another great example, if I did this carbon here, and I put 4 iodines on it, right? Or 4 fluorines, or 4 bromines, or 4 chlorines, or 4 of any of the same thing, it would be nonpolar. Doesn't matter what they are, as long as they're all the same. Okay? If any one of them is different than any of the others, it's polar. Okay? And then we'll go through some naming things to finish up for today. We'll do a lot more naming of organic compounds beginning next time, but this is the last of the review material from your other course. So when you have two non-metals put together in a compound, right? So we have some molecule that has two non-metals, right? Remember that's that top corner. We name them by naming each copy of each element and giving you the number that's present, right? So technically water, is H2O, should be written as what? What should its technical name be, right? Water is a commonly accepted name. So name the first element and put a prefix that tells you how many of them are there. so it's hydrogen, and there are two of them, so it's a dihydrogen, and then name the second element, and it's an oxygen, so dihydrogen monoxide. Right? We tend to change the latter element's ending to say oxide or hydride or sulfide. We change the more electronegative element's ending. Right? So why don't you try a few of these with me? You got to know your prefixes, mono, di, tri, tetra, penta, all the way through deca, right? 1 through 10 I want you to know. But let's try a few of them. So the first one here says S2Cl2, right? Chlorine being the more electronegative one here, so we put it second. So we say the first element first and put a prefix in front of it, and then we say the second element second, putting its prefix and changing the ending. So what would your first one be called?
Disulfur dichloride.
Disulfur.
Disulfate.
Right.
Disulfur dichloride.
Right. Exactly right. Disulfur dichloride. Okay, so you say the first name first with the prefix, the second name second with the "ide" ending, and you get disulfur dichloride. Okay, just like that. All right, what about the second one?
Carbon disulfide.
Carbon disulfide. Well, you didn't tell me how many carbons were there, right? We looked back, we said, hey, you're supposed to put that mono in front of it. If you don't tell me mono, it's assumed you said mono, right? That's just like most things when we write the formulas, we don't write a 1 next to the oxygen of water. If you don't say it, then we assume you mean 1. So in this case, you told me it was a carbon disulfide. You could say monocarbon disulfide, but we generally omit the mono when there's only 1. Okay? How about the next one? There's P4O10.
Tetraphosphorus decaoxide.
Right, so tetraphosphorus decaoxide. We kind of shortened it to make it a contraction. Instead of saying decaoxide, generally we have vowels stuck together like that, we just combine them. And you'll see that a lot when we do organic names as well. Right? Why didn't we do that with the chloride? Right, in the beginning, because chloride didn't start with a vowel. Right, so it's dichloride, right, or disulfide. But we have dioxide or decaoxide. We kind of shrink the vowels together, making it easier to say in English as decoxide. Right, and then the last one.
Carbon tetrabromide.
Exactly.
Carbon tetrabromide.
Exactly. We can leave out the initial mono again. All right, so carbon tetrabromide. We tend to not include the mono when it's describing the first of the two elements, but when we describe the second one, we often leave the mono in. Right? So when the case of water, we didn't call it dihydrogen oxide, we called it dihydrogen monoxide. So when we say the second one, we tend to leave that mono in to indicate it's 1. But for the first one, we kind of often drop it. Okay. All right, here's some other ones. Let's try these at the bottom. All right, PF3.
Phosphorus trifluoride.
Phosphorus trifluoride, good. How about the second one? SO2.
Sulfur dioxide.
Yes, sulfur dioxide, good. The third one here says P4S10. That's a lot like our third one from above. I just exchanged the oxygen for a sulfur.
Phosphorus decasulfide.
Right, tetraphosphorus decasulfide. I left the vowel in there this time because the sulfide doesn't begin with a vowel. Good. And then the last one, N2O4. So what do you think? N2O4. Sorry, you broke up.
Dinitrogen tetroxide.
So dinitrogen tetroxide. So we kind of blend it together at the end. Instead of tetraoxide, we just say tetroxide and leave off the other vowel. All right, so all those were correct. Okay. So we're finished with all of the review material. We'll start next time beginning the actual organic chemistry part of this course. And then we'll introduce some organic molecules, what they are, the chemistry of carbon. And so I would suggest reading up on it or looking at the slides before class and bring your questions to class, because it's great to have you ask these excellent questions.